That information is then converted to FC, or fire control. The first line of information comes from BSTS, Boost Surveillance and Tracking System. BSTS is a series of satellites looking down at the Earth. They are in geostable orbit, remaining over a single Earth point 22,300 miles in space. A boosting rocket creates a large, white-hot plume that is relatively easy to spot and track. The tricky part comes in the handoff from the plume to the hard body of the missile itself. The tracking is of the plume, not the missile, so any kinetic or directed energy weapon must be targeted at the booster body, not the plume. A direct hit on the plume is worthless. As an ICBM sheds its boosters and becomes a bus, it loses most of its plume, but is still hot and still carries all of its warheads. Once out of post-boost, SSTS, or Space-Based Surveillance and Tracking, coupled with ground-based radar, take over and track right through the terminal attack phase. To accomplish simply acquiring and tracking an ICBM with multiple warhead missiles demands four major components. First, you have to pick out all the missiles from all the space and Earth backgrounds of visible wavelength and infrared wavelength. Second, you have to distinguish the missiles and especially the mid-course warheads from decoys and the over 5,000 satellites and other pieces of space junk floating around up there. Third, you need a computer system that is as fast as a supercomputer, hardened against radiation and electromagnetic bursts, and small enough to be boosted, powered, and cooled in space. And finally, you need a communication system that is jam-proof and secure, or the whole program will fail. One of the toughest target acquisition jobs is finding an object against the background of the Van Allen radiation belt, or the Aurora Borealis over the North Pole. If SDI could not find a target there, you can bet that's where all the attacking missiles would come from. As early as 1986, the Earth Limb program was measuring all the phenomenology of the Earth background, including the aurora. SDI has since proven it can find the target even there. The 9-month Delta Star flight conducted well over 100 operations measuring and mapping Earth and space backgrounds to be embedded in SDI sensor memory banks. It also collected the effects of various chemicals released in space as possible countermeasures. The Queen's Match flight of 1988 collected infrared data on foreign targets as SDI continued to build its database. In 1989, the Janus experiment used high-resolution infrared imagery to collect and catalog the signatures of post-boost vehicles so future SDI sensors could compare what they are observing to a database of known phenomenology and recognize what they are looking at. Distinguishing decoys can be tough, but not impossible. The first step is to discover the different signatures of warheads and decoys. The Delta 180 series has been collecting information and helping build a database of vehicle and decoy signatures. Another way to distinguish warheads from decoys is interactively. SDI is testing methods of hitting both decoys and warheads with broad-beamed, low-power lasers. The heavier, dense warheads will absorb the laser energy and become warm or marked, while the laser energy will pass right through or destroy the decoy. Weapons guidance systems and seekers can then go only to the warmer, marked targets. SDI computing capability has grown and shrunk at the same time. SDI needs supercomputer-style capacity in space, but can't spare the room, weight, or power. While space-based computers don't need the memory, they do need the speed. Comparing a BP flight computer with a Cray-1, we see the BP has 1/3 the MIPS, or millions of instructions per second speed, but it weighs 3 pounds compared to 10,000 and uses only 28 watts of power compared to 100,000 watts for the Cray-1. SDI is working on diamond-based computer chips compared to the current silicon-based chips. Diamond chips can take operating temperatures of 500 degrees Celsius compared to 100 degrees Celsius failure temperatures for silicon chips. This means that future SDI computers can be totally solid. No need for space to cool chips. Even at the speed of light, less distance to travel means faster processing. Space-to-space communications will probably be at 60 gigahertz. This ultra-high frequency has two major advantages. It is out of the range of nuclear effects, which are frequency-dependent. 60 gigahertz is also less susceptible to Earth-based jamming. The 60 gigahertz signal, and therefore any jamming signal, is absorbed by the oxygen absorption line in the Earth's atmosphere. It would never reach space, but would be absorbed.